Okay, we're going to rationalize the denominator. This is a continuation of an Algebra 1 lesson on writing radicals in proper form. No radicals are allowed in the denominator of a final answer. Now this is kind of weird because the main reason, as far as I know anyway, is why we don't allow radicals in the denominator is that back in the days when dirt was young and so was I, we didn't have calculators, and we found square roots manually. And if y'all act up real good, that'd be a real good thing for detention, because it's a lot of trouble. So we had big long tables and charts and books full of charts that told us different square roots. The books that we had and the charts that we used wouldn't work if the denominator had a radical in it. In other words, if it was irrational. Remember, an irrational number is one that never repeats and never ends. So we want to make it into a rational number, which is one that can be written as a fraction that does repeat or end. Okay? So, and when I first started teaching this again, or started teaching it, I remembered that we did it because we had to look it up in the book. And I know you didn't have to look it up in a book. And I sit in a teacher thing, you know, with teachers, and I say, do we still rationalize the denominator? And the teacher sitting next to me was like, shocked, in horror. What do you mean? Of course we rationalize the denominator. We're going like, oh, okay. So nobody's going to take it unless it's rationalized. And here is how to do it. For example, 7 over the square root of 3 is not in proper form. It's not inaccurate, it's just not in proper form. There can't be a radical in the denominator. It could be a number, it just can't be a radical. Well, we just did this, squared, unsquared, squared, unsquared, squared, unsquared. And so what we know is that if I multiply the square root of 3 times the square root of 3, I'm going to get 3, because I square it and I unsquare it and it goes back to 3. So my goal is to have the denominator be rational, in this case 3. So I multiply it by 1. The square root of 3 over the square root of 3 is just a really fancified 1. So I multiply it by 1. I do not change the value of it. I just rearrange it, dress it up in a costume. Make it look different, but it's not different. When I do this, remember from 6th grade, the top times the top goes on to top, the bottom times the bottom goes on to bottom, and then you simplify it. So this simplifies down to 7 times the square root of 3 over 3. Now, this is where folks say, like, that's more simple than that. That looks simpler. It has less numbers. Oh, no, 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 no. This is the more simple one. This is the proper form. That's sometimes why I don't use the word simplified, because sometimes when it's in proper form, it's actually a little more complex. Okay? But, hey, this is what you need to do to get it out of it. So let's look at an example here. How about 5 over 2 times the square root of 27? Okay, there's at least 2 ways to do this. I'll start with one, and that is to simplify the radical first. I personally think that's the easiest way, easier way, but you get to choose whichever one you want. So then this would now become 5 over 2 times the square root of 27, the first way, this is my problem, becomes 5 over, okay, 27 is 3 times 3 times 3. A happy couple and a lonely only of 3. So that's 2 times the happy couple of 3 times the lonely only 3. Does everybody see that? Okay, which is 5 over 6 times the square root of 3. Oh, well, you know, I made that a little bit easier to do, but it's still irrational. So I need to multiply by the square root of 3 over the square root of 3, which is 1. Okay, so this will be 6 times the square root of 3 times the square root of 3. Well, the square root of 3 squared is 3, and 3 times 6 is 18. What is in the numerator? The top times the top goes on to top. So that's the correct form of the answer. Okay. The other way to do it, don't simplify first, which will work just fine. This really isn't a whole lot different steps. It's just which way you prefer. So we start with this. and we go ahead and multiply. To rationalize the denominator, multiply them both times the square root of 27. So that'll be 5 times the square root of 27 over, well, the square root of 27 times the square root of 7, that's squared, unsquared, squared, unsquared. So it's going to be 27 times 2, which is 54. Does everybody see that? 27 square root is 27. Square 27, unsquared, squared, sorry. Okay. So then, now we have to simplify this to write it so that there are no perfect squares under the radical. And again, we know that the square root of 27 is 3 times 3 times 3 are the prime factors. That's a happy couple of 3's and a lonely only of 3's. Happy couple of 3's, lonely only of 3's. So here's the happy couple. Here's the lonely only. All over 54. Now you can go ahead and make that 15. But remember, in situations like this, we're going to treat this portion as though it's its own fraction. When you make it 15, it's going to be over 54. Both of those to divide by 3, so it can be simplified. So why multiply it out? This will be 5 times the square root of 3 over 18 for our final version on it. Okay, here's some for you to practice on. Okay, let's see. There you go. Give these a practice. Pause the machine. And then here are the answers. Okay. Simplified radical. That's what we're doing here. We're writing simplified radicals. Okay, so here's the process that we go through to simplify a radical. There could be no perfect squares under the radical. Go ahead and write all these down. This is a summary of what I've just done. And then we have this really interesting word here, surd. I never knew this word. Surd is just a simplified radical. How, Dr. Hamilton, did you figure that out? Oh, Froggy asked that. Froggy, thank you for asking. Okay. Here's how I did it, little frog. Can you look here? Okay. See right here, this is a cup that my son gave me for Christmas one year. Got it at the British market, and this is all the British ways to talk about math, and it's really kind of fun. One of them that I really like is right here, a cuboid instead of saying rectangular prism. Isn't it just easier to say cuboid? But right here is something I had never heard of, or if I had, I'd forgotten it. And that is a surd. It's a simplified radical. I tried to Google it and figure out why they call it a surd. I asked a friend who's a British and big into mathematics, why is it called a surd? And all he told me was, because it's a surd. And I'm like, okay, because I was thinking maybe it was an acronym for something. But that's what it is. A simplified radical is known by the Brits as a surd. Okay. Now, what we have, we've multiplied and divided and we've simplified. So now we just have to be able to add and subtract. Now, this is not as hard as you think it might be. It's an application of what we've been doing all year. So go ahead and write these down, and then I'll show you some examples. This is what it takes. So if you would, pause it and write it down. Now I'll talk about it for a minute. The only time you can take things in and out of a radical is if it's a perfect square. Otherwise, you just think of it as this big block that you just got to deal with. And it's not a variable, but if you think about it in the same terms as you would think about x and y, sometimes that helps people to figure out how to do it. You can't mix the two. Near the twain shall meet. So if you just think of this as 3x and 4x, then you notice that they are not like terms. Remember, in our variables, all of the variables and the power of the variables had to be identical to be able to combine like terms. See, all we're doing here is combining like terms. You already know how to do that. We're just applying it to the radicals. And here on the radicals, it works the same, but it's different, of course. And hopefully you'll be able to do it. Let's try a few. So what I'm saying here is, just like you can't add 3x and 4y, that's as simple as it'll get. 3 times the square root of 5 plus 4 times the square root of 2 is as simple as it'll get, even though it really doesn't look all that simple. So let's look at a few of these. How about 6 times the square root of 2? 6 times the square root of 2 plus 2 times the square root of 2. Well, here you got 6 of them. There you got 4 of them. Whatever it is, you got 6 of them, and you got 4 of them, and they're the same. It must be 8 of them. Right? Works like a radical. Well, how about the square root of 5 minus 6 times the square root of 5? Well, you've got one of them here. Remember, there's a 1 there. You can write it if you want. And you're taking away 6. Oh, my goodness, you must owe 5 of them. Okay? And how about a little bit of distributive property action? What if you have the square root of 6 times 7 times the square root of 3 plus 6? Okay, we're just going to do our usual multiply them separately. So this will be the square root of 6 times 7 times the square root of 3 plus 6 times the square root of 6. We always put the number multiplied first. That's just good grammar. Okay. Within this term, this is all multiplication. Multiplication is commutative. It doesn't matter what order we do it in. 7 times the square root of 6 times the square root of 3. Here we have the product of the radicals is the radical of the product. So I can rewrite this as 7 times the square root of 18. Oh, you know, I wonder if 18 has any happy couples in it. I'm thinking that's 3 times 3 times 2. Yep, that's 18. Oh, look, a happy couple and a lonely only. Happy couple goes out on the town. Lonely only stays home and watches Netflix. So this will be 7 times 3 times the square root of 2, or 21 times the square root of 2. Did I do that right? 3 times 3 is 9, yeah. Okay, so our final answer then would be 21 times the square root of 2 plus 6 times the square root of 6. That's as simple as it'll get. Beyond there, nothing goes. Okay, again, pause and practice. Okay, pause and practice a bunch of these, and then come back and look at your answers, see how you're doing. Okay, here are the answers. And we'll do it again. Okay. Now these are going to get a little more dicey, right? Let's look at some of them. For example, let's work this one right here. 52, let me work that one for you. Okay, you got it? Okay, 7 over the square root of x plus 3 over 2 times the square root of x. You can either rationalize the denominator first or find a common denominator first. Doesn't matter which one you do. Let's find the common denominator first. Here, this denominator is 2x, 2 times the square root of x. If this were 2 times the square root of x, we could add that. Remember back to your 5th grade fractions. If the denominator is the same, you add the numerators. If the denominator is not the same, you can't do it. Okay, what I want to do is multiply this by 2. To be allowed to do it, I need to do the top to form an equivalent fraction. And then what we'll have is 14 over 2 times the square root of x plus 3 over 2 times the square root of say, no, you're not used to looking at fractions that look like that. But go back to the basic principle that you learned in 5th grade. If the denominator's the same, add the numerators. It still works, even though they're really weird-looking denominators. So the denominator is 2 times the square root of x, and the numerator is 17. Wait, I have an irrational denominator. I have to rationalize it. I want to multiply the denominator by the square root of x. I'll square it, unsquare it, square it, unsquare it, and that'll get me back to x, because the square root of x times the square root of x. To be allowed to do that, I must do it, to the numerator as well. So that equals 1. I'm just multiplying by 1, so I didn't change anything. Notice I don't have to multiply by the whole denominator, only the irrational portion, okay? Only the square root. If you multiply by 2 and put another 2 here, it'll still work, but it'll be more steps, because at the end you're going to have to simplify and reduce your fraction. So then what do I have here? 17 times the square root of x over 2 times x. Okay. So give these a try. And here's the answers. Oh, and if you're just really a glutton for punishment, here's just some more you can practice and try. Okay. Give them a go. Now this one right here is plumb weird, and so is this one. Let's talk a little bit, but this is really pretty complicated, all of these. Let me explain it to you. Look what happens. Let's just take this one right here. 2 over 5 minus the square root of 3. You say, well, I'll just multiply by the square root of 3. Okay, well, let's try that. Multiply by the square root of 3. Remember, it has to be the whole denominator, not just this portion. I'll multiply the whole numerator, which is just 2, by the square root of 3, and I have to multiply the whole denominator. Let's see if that took care of our problem. Remember, our problem was having a radical in the denominator, having an irrational denominator. So now the numerator will be 2 times the square root of 3 over, oh look, 5 times the square root of 3 minus 3. Notice we did not accomplish our goal. Our goal was to have no radicals in the denominator. There's one right there. It didn't work. That's right. It didn't work. So then what are we going to have to do? Okay, we'll forget this. Think back when we were doing factoring. Think back to difference of squares. Remember all the different ways we factored, and this was a special case where if you had a perfect square and a difference, subtraction, that you could do it with the square root, and then that would take care of it. Okay, so let's see what happens here when we do that, and then the middle term drops out. In each case, with the difference of squares, we had the same two things here, and one of them was a minus. That didn't do that very good. So we'll say something plus something, doesn't matter what it is, and then something minus something, the same something. The two front ones are the same, the two back ones are the same. If there's a plus and a minus, what happens when we multiply it out is the middle term goes away, and all we get is perfect squares. It'll be the perfect square of whatever the star is and the perfect square of whatever the triangle is. So what we're going to do here, we're going to say 5 minus the square root of 3 times 5 plus the square root of 3 using the difference of squares. But we're using it backwards. When we did it before in factoring, we started with the squares and then came to the square roots. So we're going to work backwards and find it now. So 5 times 5 is 25. 5 times square root of 3 is plus 5 times the square root of 3. Negative minus 5 times the square root of 3 minus 3. Okay? Yeah? 5 times the square root of 3 minus 5 times the square root of 3. So our denominator is 22. We go back to our original fraction. It's 2 over 22, which is 1 over 11. So whenever you have an add or subtract in the denominator and you're trying to rationalize it, you're going to have to use the difference of squares. Go ahead and practice on these. Go ahead, pause. And here are the answers. And here ended the lesson. Have a good night and stay safe.